Hello students, now in class 11th I told you about the forced or drive-in oscillations. Now today I will tell you about the damped oscillations. Damped oscillations. When an oscillator oscillates under the effects of damping force, its amplitude of oscillation decreases continuously with time. Such oscillations are called damped oscillations. Damping force means the frictional force or the viscous force. Damping force means the force that opposes the oscillations. Motion of oscillator. For example, the frictional force, viscous force, etc. So all these forces always oppose the motion of the oscillator. Because of that, its amplitude decreases, because the energy of the oscillator also dissipates in the form of heat. Due to damping force, the energy of oscillator dissipates continuously. So we can show them by this figure. With time. The figure below shows damped oscillations. This is the 0, here we take the x, this we take the time, then initially the amplitude is so much, then this will decrease, and you can see that this is initially the amplitude was so much and then it decreased and then again decreased and finally the oscillator stops the motion. So the following forces acts on oscillator. Number 1, restoring force F1 equal to minus Kx, where K equal to force constant. Second, damping force F2 equal to minus lambda V and F2 equal to minus Vm, lambda equal to constant and V velocity. Velocity of oscillator. The damping force is always the velocity dependent. It is the function of velocity. So because of that we are having the velocity of the oscillator. So the total force F equal to F1 plus F2. So F is d2x upon dt square equal to minus kx minus lambda v. Or we can write it d2x upon dt square plus k upon m into x plus lambda upon m into dx upon dt equal to 0. Here the v is equal to dx upon dt. So we write down to this d2x upon dt square plus omega naught square x plus 2r dx upon dt is equal to 0. Where? So this is the differential equation of the damped oscillations. It is differential equation of damped oscillation. Now here we have taken where omega naught square equal to k upon m, and it is called the natural frequency. The natural frequency of oscillator, and this 2r equal to lambda upon m, where this r equal to coefficient of damping, coefficient of damping. So this is the required equation of the damped oscillations. Now you can see the solution of this equation. The solution of above equation. That is equal to x equal to a e to the power minus lambda t upon 2m into sin omega t plus phi, or x equal to, this we take a constant small a in place of that. So this is equal to a e to the power minus lambda t upon 2m into sin omega t plus phi. This is the solution of this equation, where a equal to a e to the power minus lambda t upon 2m. This is the amplitude. And this omega equal to frequency of damped oscillator. Damped oscillations. You are seeing that here we have a term E, this is the exponential. It means that the amplitude decreases exponentially. So this is what I show you, that in the just in the figure, that the amplitude goes on decreasing, and that it is following the principle of this law of exponential. Clearly, the amplitude decreases exponentially. Decreases exponentially. So what that I have shown you in the figure earlier also. This A is a constant here, this A is constant. And now this omega. Frequency of damped oscillations is given as this omega equal to square root of k upon m minus lambda square upon 4m. This is the frequency of this damped oscillations. And now if you put this value, then we can have this omega equal to square root of, now k upon m is equal to omega naught square minus lambda square upon 4m. So we are having the lambda upon m equal to your 2r. So this is now 4r square. So this is now r square. Where omega naught, omega square equal to k upon m and lambda square upon 4m is equal to r square. So this is the frequency. Either you write to this one or you write to this one. This gives you the frequency. And you can see from here, if r equal to 0, then omega equal to omega naught. It means what? That if the damping is 0, it means the oscillator is vibrating, is oscillating freely, then its frequency will be equal to its natural frequency. It means in absence of damping force, the oscillator oscillates with its natural frequency. And it is also clear from here that because of this r square, this frequency, the damped frequency, is always less than the natural frequency. Also, omega is less than omega naught. It means what? The frequency of damped oscillations is always less than its natural frequency. This is because we are having this r square. So thus the frequency of the oscillator decreases exponentially with time. And now energy of damped oscillator. E is proportional to, as we know, this is proportional to A square. So energy E equal to this, we put the value of this A, so this is proportional to e to the power minus lambda t upon m. And you can easily see that the energy decreases exponentially. Energy decreases exponentially. So how to show it to like this? This is, suppose we are having the energy, and this is now time t, and you can see that this will decrease like this. This is the maximum energy of the this oscillator, and then it goes on decreasing continuously with the time. As we are having the factor t, so energy decreases exponentially. So whatever oscillations happen in the nature, they all are damped oscillations, because every particle or every body is oscillating in air. So this is the friction due to the air. But since the damping due to the air is less, so particle continues to move for some time. And you can see that if it is left freely to move, then after some long time it will come to the rest position. And when the oscillator oscillates in, suppose, some liquid, then damping is very high. Because of that, it cannot vibrate, it cannot oscillate for a long time. So depending upon the nature of the medium, the damped oscillations are either dead quickly or dead in a long time. So all the mediums have this damping force. This may be the frictional force, or it may be the viscous force. You can also observe that suppose you are in a school and bell is going on, you will listen the sound of the bell. But when the hammer stops to strike with the bell, then you will listen no sound at all. It means that the oscillations of that dead because of the friction of the air. You can see that whenever you are speaking to somebody facing you, though the next person will listen your voice till you are speaking. If you stop speaking, he will not listen your voice. This is due to the damping of the air. So damped vibrations, they are very helpful, and you can see that because of them it avoids the noise in the atmosphere or also in our houses. You can see that if some people are speaking, and they stop the speaking, then no voice can be heard because of the friction of the air. So every particle who is oscillating in the air or in some liquid medium, then its vibrations, its oscillations are damped and they no more exist after some time. So these damped oscillations, the friction in the air and that in the liquid is very essential. Otherwise, our atmosphere will be full of sound and we will be deaf because of we cannot listen the voice for a long time. You can see that if the intensity of the sound is very high, then it creates the irritation in the human beings. So damping is essential. This must exist. So this is what about I told you about the damped oscillations. So you like, share and subscribe this video. Thank you.